And then we define another quantity which is called the proper distance, or the physical distance. This is a function of time. In this case, we integrate ds, okay, ds, not d sigma. So this is what I've written here, integral of ds. And remember, for the spatial part, you have gij, not gamma ij. Okay, because I'm talking about the four-dimensional space-time metric. So gij, dxi, dxj. And if you do the integral, because gij is equal to gamma times a, gij is equal to gamma ij times a as a function of t, which will go out of the integral because, I'm sorry about this, there should be a square root in both of them. So this a of t will come out of the integral because it is not a function of distance, co-moving coordinates. And when you integrate the co-moving coordinate, you get back the sigma. Okay, so the physical proper distance, d, is actually the co-moving distance times the scale factor. Okay, the physical distance, which changes with time, will be equal to the scale factor times the fixed or time-independent co-moving distance between 2 points. Okay, so these are two important terminology to be kept in mind. All right, so one last remark I would like to make in the context of the Robertson-Walker metric. So Robertson and Walker were not the first person to arrive at this form of the metric. I think the first person to arrive at this form was Alexander Friedman, the Russian, the Soviet physicist, and then the Belgian priest Robert Lemaitre, who also arrived at this metric. But they were starting from Einstein's field equation. They wanted to solve for the cosmological metric, and they obtained these as solutions to Einstein's field equations. On the other hand, Robertson-Walker's analysis is much more general. They do not start from any field equation, just as we have done. We have followed their footsteps. Just from symmetry arguments, we are able to write down this form. Okay, so in that sense, Robertson-Walker's derivation is much more general and doesn't rely on general relativity at all. Okay, so this is an important distinction, because if you come up with the theory of gravity which is not general relativity, and there are many, for example, Brand's-Dickey theory is another theory of general relativity, which is based on a space-time metric, except for the Einstein field equations, you get some different equation. Now, Robertson-Walker metric form will be a solution to that as well, because this form is dictated entirely by symmetry, not by what is the particular equation, not by dynamics. Okay, so the fact that this metric is of kinematic origin can be traced back to the work of Robertson-Walker. On the other hand, Friedman and Lemaitre, they derived it as a solution to some equation. Okay, not as some generic form, but a special equation which led to a special field. All right. With that point, I will conclude the discussion of the Robertson-Walker metric and move on to some interesting physical consequences of this. The first thing we will see is that the Robertson-Walker metric leads to the Hubble law for the recessional velocities of galaxies. Most of you have read about this in elementary school, that when we look at distant galaxies, they seem to have undergoing high redshifts, extreme redshifts, that is, they are moving away from us, and the velocities, in fact, grow with distance. So the farther the galaxy, the faster it is moving away from us. So that phenomenological equation is known as Hubble law for recessional velocities. And we will see that it is a natural consequence of the Robertson-Walker form of the metric of the universe. Okay, let's compute the rate at which two co-moving observers, that is, observers whose co-moving coordinates are fixed, are moving apart. Okay, their rate of separation. So the rate of physical distance growing is given by, so this is the v sub r is for recessional velocity, is the rate of change of the physical distance between them. And as you know, d, we wrote that to be a of t times sigma. But because these are two co-moving observers, their sigma coordinates their co-moving coordinates are not changing. As a result, the co-moving distance between them is also not changing. So the time derivative will only act on the scale factor. Remember, dE is equal to A times sigma scale factor times co-moving separation. And when I take time derivative, it will only affect the scale factor because their co-moving coordinates are fixed. Time derivative will not act on the second term. So we have this equation. Now this equation we can write a bit more very differently by dividing and multiplying by A. And then A times sigma I can call D. Okay? And this ratio, A dot by A, I'm calling h of t. So this is the ratio. So we get a law that the recessional velocity at time t is equal to some function h of t, which is this ratio of the time derivative of the scale factor to the scale factor itself, times the physical distance at time t. Okay, so this is the Hubble law that the velocity of recessional velocity is proportional to distance. Of course, this is not proportionality constant is not really constant in time; it's a function of time. But let's consider the present epoch. But before that, let me call this h of t has a name. We call it the Hubble parameter at time t, and it represents the instantaneous rate at which a pair of co-moving observers, unit proper distance apart, at time t are being moved apart by the expansion or contraction of the universe. So we have v of r of t, h times d of t. Now, if this is equal to 1, then the velocity is equal to h of t. So that's what I meant when I said that unit proper distance apart, the velocity is same as the Hubble parameter. So it is defined to be the rate of separation at unit proper distance. Now, at the current epoch or present time, let's say t equal to t0, which is right now, the Hubble parameter is called the Hubble constant. H at t0 is called h sub 0, which is the Hubble constant. Now, from observations of Hubble and some astronomers before, we can compute that h0, this Hubble constant, is around 70 kilometers per second per megaparsec. This is a bit strange units, but it completely makes sense for galaxies because the distances is of the order of a few hundred megaparsecs. So this is, although this seems weird at first glance, this actually makes sense. And this value is around 70. Now, there is some controversy in recent times regarding the exact value of the Hubble constant, and there is some disagreement in the literature. So I'm not going to tell you, I'm not going to prefer any one of the experimental figures as such, and I'm just going to say that this is around 7. What is the exact value? We don't know. And this problem is known as the famous Hubble tension in cosmology, that we seem to have not determined the Hubble constant to exactly. So nevertheless, for our intents and purposes, in our case, it would be around 7. Okay. Now, so at current time, what we have at the recessional velocity at current epoch is the Hubble constant times the physical distance between the galaxies or between two co-moving observers. And this is something which is known as the Hubble law, which Hubble experimentally arrived at in 1929, and also was because, as I mentioned before, Friedman and Lemaitre had already used general relativity to solve for the scale factor and the metric of the universe. They also arrived at this result. This is known as the famous Hubble law. Again, it just follows from kinematics. You don't need any in general relativity to determine it. It's just the form of the metric, the Robertson-Walker form, naturally leads you to the Hubble law. And actually, remember, this is positive, 70 kilometers per second. So this is positive, we determined. That means the scale factor is actually a increasing function of time. So this you can think of derivative of log of A, ddt of log of A. And since this is determined to be positive from observations, that means A is an increasing function of t. So number is equal to some number, let's say c, which is positive. So this is t raised to the c. The c is a positive number. That means it's an increasing function of time. Okay, so the universe is expanding. Two co-moving observers, as time goes on, they're going apart. Now, of course, when Hubble did his experiment, he was looking at galaxies, and that means we are assuming that galaxies are co-moving observers. That is not always the case. For example, if we look at Andromeda galaxy, I think it will give you a negative relation because it undergoes a blue shift. I will come to that a bit later. So, but the assumption is that large galaxies which are very far away, most of them are co-moving observers. And there is a reason for that. I'll come to it in a second. Right, but let me point out to another interesting fact that comes out of this Robertson-Walker form of the metric and the Hubble law, which is the notion of a cosmological horizon. The fact that the part of the universe which we can observe, the observable universe, is finite in extent. And the reason is that if we look at distances, galaxies are objects which have separated by a proper distance, which is greater than c over h naught. The velocity, the recessional velocity, is larger than c, the speed of light. That means the distance between those two co-moving objects is growing at a rate faster than the speed of light. So if light starts out from one of the objects, it is never going to make to the other because the intervening distance is always going to grow at a rate faster than the speed of light. So light is never going to overcome the distance. Okay? As a result, they will not know about each other because light from one cannot reach the other. So light from objects at or beyond RH, which is the special distance, c over h naught, would not reach us. And we will say that centered around us, if I draw a sphere of very large radius with radius RH, we will never be able to see objects which are outside this because light from this will try to reach us, but the intervening distance will grow at a rate faster than the speed of light, and hence light will never be able to reach us. Okay, so we have a horizon associated with us with the radius given by this ratio, which is called the cosmological horizon, and beyond that, whatever the universe is, we will never be able to observe. So the observable universe is actually finite. We don't know if the full universe is finite, that we do not know, but this much we can say is that the observable universe is finite. And that is up to the cosmological horizon. If you plug in the numbers, like h0, we already mentioned h0 to be 70 kilometers per second per megaparsec. If you include that, then this cosmological horizon turns out to be at a radius of 4,300 megaparsecs, so a bit more than 4,000 megaparsecs. We cannot observe things beyond that. There are objects probably, but we will never be able to know if they exist, because light from those will, at the current rate of expansion, light will never reach it. Of course, it might happen in the future that the expansion rate of the universe decreases, and as a result, the separation between co-moving observers, which are this distance apart, becomes less than the speed of light. Then light will be able to reach it. But for the time being, if the acceleration of the universe continues as it is at the present scale, we will never be able to get light beyond that. So this is RH is sometimes also known as the horizon scale or the Hubble distance. And as I said, it quantifies the size of the observable universe. Now one can also introduce a notion of a time, which is called the Hubble time. This is by dimensional analysis. Once, if you have distance, then if we can divide by the speed of light, that gives you a time. If you divide by c, both sides, then that gives you a notion of a time, which is called t sub h, which is equal to the inverse of the Hubble constant. is called the Hubble time, and it represents a time scale for the current universe. It turns out, if you plug in the numbers again, this is close to that figure which you hear about in popular science, 13.4 or something billion years. I'm approximating it to 14 billion years, or 14 giga-years. Okay, so naively, this can be thought to be as the age of the universe. So why do I say naively? It's because is that the Hubble parameter is not a constant; it's actually a function of time. But let's say this is a constant. Let's assume, for simplicity's sake, that this is constant equal to h0. That is the current day Hubble parameter, or the Hubble constant. In that case, we can easily integrate this expression v equals hd, right, and v equals d dt. So this equation can be immediately integrated for d, and then this time will be the time at which the universe started. All the co-moving objects, where distance between them vanished. The proper distance between co-moving observers becomes 0. Okay, and then the universe is expanding at a constant rate. And if you time reverse it, it will then there is a time from which from the current time there is a past time at which all the co-moving observers coalesce to a single point. That would be the Hubble time. So it's a very nice picture of the universe in which the Hubble expansion or the Hubble rate is constant, and we back evolve it to a point where we can see that the proper distance vanishes. Again, we just need to integrate this equation, and you'll get an exponential kind of solution. And you can ask when this is 0, and this time h will be something like this. Okay. So this Hubble time is thought to be as a kind of an estimate of the age of the universe, provided the scale factor doesn't fluctuate wildly, and we don't know that. So naively, it is the age of the universe. All right. Now let me spare a thought about atypical observers. For example, us Earth-bound observers, or in the Milky Way. Okay, and the notion of peculiar motion associated with it. So let me revisit. Consider a pair of observers, not necessarily co-moving. So their co-moving coordinates are changing as the universe evolves. So they're not fixed co-moving coordinates. Okay, they do not have that. So the co-moving distance between them is also not going to be a constant anymore because their co-moving coordinates are fluctuating. So the co-moving distance will also fluctuate. It won't be time independent. And examples of such are the solar system in the center of the Milky Way. Remember, the solar system is orbiting the center of the Milky Way. So even if the universe isn't expanded or contracted, it would still go on to the solar system's co-moving coordinates with respect to the Milky Way will not be the same. Okay. Similarly, Earth going around Sun. So these are not pair of typical observers because their co-moving coordinates are changing. Now, if you have such observers, you can compute the relative velocity between these two. Again, the relative velocity is defined to be the rate of change of physical distance between them. Remember, the physical distance is a times sigma. And both of them now are functions of time. As a result, you'll get two terms, a dot sigma plus a times sigma dot, which I've written to distinguish them in two different color fonts. The first term is, of course, the usual term which I wrote down below before. And the second term is actually new, which I've distinguished in red fonts, is the one in which carries information about how the co-moving distance is changing with time, d sigma dt, okay, and then multiplied by the scale factor. So this I'm going to denote by v sub t, and this is the usual recessional velocity due to the expansion, which is v sub big R, which we had introduced before. So it now has two components. The first term is called the Hubble flow, because had they been co-moving, they would flow along with the universe. So this is called the Hubble flow. and this is caused by the expansion or contraction of the universe. The second term is independent of the evolution of the universe, and it is caused by interaction between local systems, like, for example, the gravitational force between Earth and Sun, not a large-scale behavior of the universe. So the second term is called a peculiar velocity or peculiar motion. Okay, Hubble flow, and then if your moving coordinates are changing, then that gives rise to something called a peculiar motion or peculiar velocity, and some texts also call it particular velocity or particular motion. Right? For atypical observers, you have to deal with the Hubble law will be modified because there will be an extra term. For gravitationally bound systems, for example, planetary systems or stars which are moving inside galaxies, it turns out that the second term is much larger than the Hubble term. Okay, second term turns out to be much larger for gravitationally bound systems. Okay, but if we zoom out, if we make the distance larger, as you can see, the second term is proportional to distance. So the Hubble term will start increasing with distance. On the other hand, the peculiar motion term is not a function of physical distance, so it will stay as it is. So if we zoom out into intergalactic space, that is, now we're talking about distances which are equal to the separation between the galaxies, huge distances, a few hundred megaparsecs, then the Hubble flow velocity v sub r, which are proportional to distance, will dominate over the peculiar motion, and the peculiar motion will become irrelevant almost. For megaparsecs, few hundred megaparsecs level, this Vp is much smaller than the Hubble flow. And for galaxies at large separation, when we are looking at two galaxies at large separation, the peculiar motion is completely unimportant, and it's entirely, the dynamics is entirely Hubble flow. Okay. So this is what I mentioned, that when Hubble plotted his plot of velocities with distances, it appears to be the straight line only if you take the first term to be so large that the peculiar term can be neglected. And so for very large galaxies, the second term can be neglected, and you have the Hubble law. But for close by galaxies, for example, Andromeda, the second term might be actually larger. And for those cases, you will not see, you'll see a deviation from the Hubble law. All right. So asymptotically, all far off things will approach the Hubble flow. Right? Asymptotically meaning very large distances. Everything will be just the Hubble flow. The peculiar motion will be completely irrelevant. All right. With that note, let me go to relation, which again follows from the Robertson-Walker metric, just kinematics, no dynamics involved here, no Einstein general relativity, Einstein field equations have been involved here, and it still gives us something. So as I said, the way Hubble determined the recessional velocities is by looking at the Doppler shift of light emitted by those galaxies, distant galaxies. Remember the Doppler shift Z, we've defined it to be the observed minus the emitted wavelength divided by the emitted wavelength. And from relativity, you know that the Doppler shift Z is equal to the fraction of the velocity of the source with respect to the speed of light. Okay? So if you assume this relation, then the redshift is equal to the Doppler shift, which is V over C. So if I plug this, if we take this to V to be the recessional velocities, and if I plug the Z equals V over C in the Hubble law, then we get, so let me just write down, the Hubble law is V equals H naught D. And then divide by C, C cancels. So I'm sorry, so we have Z equals H naught D over C, which is this. So this relates the redshift if we see the galaxy, and D is the proper distance to the galaxy. Okay, and then the proportionality constant is H naught over C. If you plot the redshift with the distance, which Hubble did from data, you should get a straight line passing through the origin, and so the galaxies will lie on this, more or less, and the slope will be given by, the slope of this will be given by h naught over c. Okay. So this is an alternative form of the Hubble law. Usual Hubble law is recessional velocity with distance, but here I'm looking at redshift as a function of this. All right, so we probe a little deeper, and let's determine the redshift from the Robertson-Walker metric. We know the Robertson-Walker metric. From that, we should be able to compute the gravitational redshifting, or gravitational Doppler shift easily. And let's do that. So then we will determine the z what comes from theory. Let's see what we're getting. Now let's consider 2 points. One is emitting T. There is an emitter which is sending light to an observer O. So one needs to consider then light-like geodesics joining the points O and E. I'm sorry, this is the emitter E. So one needs to consider light-like geodesics because they must, O and E must lie on light-like geodesics. And if it is a light-like geodesics, the metric separation space-time interval must vanish. Yes, in the Robertson-Walker metric, this will be equal to 0. So dt must be equal to 80 sigma, which is what we had. Right. So I've brought back the factor of c here, but you can put it to 1 if you want to work in natural units. Right now I'm using SI units, so I've brought back this factor of c here. So the Robertson-Walker metric vanishing condition gives us d sigma equals c dt over a. So this is going to be true for any 2 points on the light-like geodesic. Now consider a light wave that is the crest of the wave, which is emitted at a certain time t sub e, and that crest of light is observed, or it reaches the observer at time t0. Then the co-moving distance between the 2 observers, to the emitter and the observer, sigma, is given by this. All right. So we're looking at 2 co-moving observers which are evolving with time, of course. And then one of them sends a light ray to the other. And let's say at t of O, the crest of the wave, let's say, the diagram, but yeah, the crest of the wave, and the crest reaches, the maxima reaches at some TE. Then we have this relation, the co-moving distance is equal, due to this formula, one can integrate this, and the co-moving distance between the 2 points will be given by this formula. Okay, from TE to TO, you need to integrate this side, and you get this formula. But remember, these are co-moving distances, and co-moving distances for co-moving observers do not change. Okay, so now consider the next crest. So a light wave, you have a continuous set of crests and troughs, and one crest is left, and then you have another crest coming out of the. Sorry, this should be over. The second crest will leave at after one time period, which is given by the wavelength by c, TE by c, and the second crest will reach the observer TO at one time period later, which is lambda over c. Okay. So then, in that case, the co-moving distance will be given by the exact same formula, except T and TO are replaced by T plus lambda E over C, and TO is replaced by lambda O plus TO plus lambda O over C. So I can write down the second equation, which is exact replica of the first, except the limits of integration differ by half a wavelength divided by a time period. So now we'll do some manipulations in which the first equation which we had for sigma, this I'm going to split up the 2 integrals. So this integral and the second integral, we're going to split it up into two integrals. So from TE to TO, instead I will write it as from TE to TE plus half T plus lambda E over C plus T plus lambda E over C to T naught. Okay. So I'm dividing this range into two. And then similarly for the second, I'm also going to divide it into two range. So lambda E plus TE plus lambda E over C. First I will take it to T0 and then from T0 to the final upper limit. Okay. And because they are both co-moving difference, these two integrals are the same. And from these two, we can see easily 2 points just cancel out. They are the same thing. And then we have integral over one time period. So TE times TE plus lambda over C. So integral of this same thing over one time period during the time of emission, around time of emission, is equal to the integral of the same quantity at the time of observation for this crest to crest. Okay, crest to crest time of observation. These two integrals are the same. This integral and this integral are the same. And if I assume, because one time period is a very short time compared to the evolution scale of the universe, the scale factor remains almost constant during this time, and I can take it out of the integral. In both cases, take it out of the integral. Then we get this side would be integral of dt, c dt will give you lambda e, and then integral of dt times c will give you lambda o on both sides, onto the second side. And then we have the denominator, as I said, that I'm assuming that the scale factor doesn't really change appreciably in one time period. So from this, we can write the ratio of the observed wavelength to the emitted wavelength to be the inverse ratio of the corresponding scale factor. Okay, the scale factor of the corresponding time of times of emission and absorption. All right. So from this, we're very close. Now we can just write down in terms of the redshift. Remember, the redshift z is defined to be lambda 0, lambda o minus lambda e. By lambda e, which is same as the ratio lambda o over lambda e minus 1. And if I add plus 1 to both sides, z plus 1 is same as the ratio. Z plus 1 is equal to the ratio. So I'm just going to substitute here z plus 1, and we arrive at the famous redshift scale factor relation. 1 plus z, z is the redshift, is equal to the ratio of the observed, ratio of the universe at the time of observation to the scale factor of the universe at the time of emission. Now, by convention, the present day scale factor A of K0 is said to be 1. This is a convention which is widely followed. Then this redshift scale factor relation becomes simpler. 1 plus g is equal to A inverse of TE. That is, the redshift of the light we observe today plus 1 is equal to inverse of the scale factor at the time of emission. And as I've mentioned here, this is regardless whatever happens between emission and observation. The intermediate times play no role here. Okay, so the universe could have gone some crazy motion. It doesn't matter. What matters is the redshift we observe now immediately tells us about the scale factor at some time of emission. In fact, scale factor is not something we can directly measure, but this is the indirect way. This formula is impressive because it indirectly tells us what the scale factor was at the time of emission, but looking at just observing the redshift today. Now, when we look at a galaxy of redshift, very high redshift, like 1000, so in that case, this relation, redshift scale factor relation, tells us that the scale factor, so this is 1000, then the scale factor is the inverse of that, so 10 to the minus 3, 1000. So we are looking at a time when the universe was 1,000 times smaller. When you look at a galaxy which has a redshift 1000, we are looking at the galaxy as it was when the universe was 1,000 times smaller. Now, if we assume the scale factor of the universe had varied monotonically in the history of the universe with cosmic time, then one can use the scale factor as a proxy for time itself, as it is done in practice. Okay? There's no way we can determine the cosmic time, but the scale factor tells us, if we assume that the scale factor had increased monotonically with time, then the scale factor itself is a good measure of time itself. The higher the lower the scale factor, lower is the time, earlier is the time. Okay, so we are going to use scale factor as a proxy for time itself. All right, well, with that, we are at the point where we can conclude our lecture. Let me give a summary and provide the outlook for the lecture. So our aim was to apply general relativity to describe the large-scale structure and dynamics of the universe. For that, we needed to write down the metric. And the metric was constrained by the so-called cosmological principle, which we introduced, that the large-scale universe appears to be spatially homogeneous and isotropic to typical observers. And then, using this cosmological principle, we were able to write down the metric on spatial sections, and using that, we were able to choose a gauge called the synchronous gauge or synchronous coordinate system, in which the metric of the universe acquires a very simple form, which is called the Robertson-Walker form or the Robertson-Walker metric for the universe, and it has only one unknown function of time, namely the scale factor. There are two other unknowns, but they are not functions of time, the kappa and the scale of the spatial section, scale of the curvature of spatial sections. These are also undetermined, but they are not functions of time. And they're once chosen, they remain throughout the history of the universe. And then from the Robertson-Walker metric, we drew some interesting conclusions or inferences, namely that we obtained the Hubble law for recessional velocities, that two co-moving observers would appear to drift apart at a rate which is proportional to their instantaneous proper distance or separation between them, proper separation. And we also used the metric to find out for light like GD6, we have an expression for the redshift of the light emitted directly from the metric, which happens, as most of you know, due to gravitational time dilation or gravitational redshift. And that is related to the scale factor. So, of course, because this is gravitational time dilation or gravitational redshifting, it should be a function of the metric, which is, or in this case, the scale factor. This is a very important relation because, as I mentioned, just by looking or observing the redshift, we are immediately able to determine the scale factor at the time of emission. Okay, there is no direct way to measure the scale factor, and we rely on these kind of relations to extract information about the scale factor. And this is a very important relation in that respect. So up next, we will include dynamics. That is, we will write down the Einstein field equations with the Robertson-Walker metric as an ansatz and determine A of t for certain cases of matter. So we have to put in right inside one non-be 0 because we have to put stress and non-zero stress energy tensor. And then this equation will determine this function A of t. Also, they will have to determine kappa and R naught. So those equations are called the Friedmann equations, and we will look at solutions as well. All right, thank you very much for your attention, and I'll see you next time.